Hello everyone. Today I'll be speaking about a technology that is very commonly used in sound devices nowadays. What makes it relevant for us is it's also in our headphones. This technology is known as adaptive noise cancellation. Now, when we want to do noise cancellation, there are two ways of doing it. The first being passive noise cancellation, which basically is a form of physical cancellation of noise which uses some sort of padding to physically eliminate any noise that comes from the outside. The second option we have is active noise cancellation, which uses a mic to generate an anti noise signal which acts as destructive interference and cancels out the noise. An adaptive noise cancellation is just a step up of that. But if active noise cancellation exists, then why do we need adaptive noise cancellation? The reason being is active noise cancellation is based on an ambient noise, which is basically a set range of frequencies. And we know that the environment is not constant around us. Real systems have noise that is unpredictable, time varying, and over a broad range of frequencies. Now, the whole goal of sound devices is to ensure that the signal is clear and the signal integrity is maintained at the end point. Now, this technology uses the basic principle of adapt and overcome. It's basically measure from the surroundings, modify, and correct the error. Now, the underlying essence of this technology lies in three aspects. The first is creating disruptive interference, using filters, and minimizing the error, the details of which we will come to in the further slides. If I was to explain this in a real life example, let's say we take your headphones. Now, in your headphones that have adaptive noise cancellation, there's a reference mic that measures the ambient noise. Then, based on the input from the reference mic, there is a device that generates an anti-noise signal to invert that very noise. Now, in real life, the actual inverted noise waveform that is generated is not exact. So there's another mic that is closer to your ear which monitors what you are hearing. And that error is subtracted from the noise signal that is generated to fix the error in the noise. And then the next time the noise signal is generated, it's more accurate. And at the end of it, the anti-noise signal or the inverted noise signal cancels out a noise that is generated from the outside source, and the same clear music is heard by you. Now we come to the nitty-gritties of that very system. Here is a block diagram that represents that very system that generates the anti-noise signal. So now here we have a signal source, say the music that you're listening to. This speaks as the primary input. This is the noise source that is generated from the outside, and it adds a certain number of noisy signals that is added to your initial input. This forms the primary input. Now, the same noise signal is a reference input to the mic that we spoke about, which further goes to the adaptive FIR filter. So now this adaptive FIR filter generates an filter output which is subtracted from the original signal source, and then the error is fed back into the FIR filter to fix the filter output again. And this error minimization technique reduces the difference between the actual noise that we generated and the noise that is coming from the outside, so that the destructive interference is of quality. Going in further detail, mathematically, there is a way to go about this. This is known as the Wiener solution. This is a theoretical solution which tells you the most optimum set of filter weights that give you the minimum possible error. Now, the formula that Wiener solution provides is the optimum filter weight is equal to R inverse P. R inverse is the autocorrelation matrix of the reference input, and P is a cross correlation between the desired signal and the input that we provided. But the problem here is this data must be available beforehand for us to calculate the optimum filter weights. But in real systems, we won't have that data, which means we don't have R or P. So that brings us to the LMS algorithm, or the least mean squares algorithm, which iteratively estimates the weights till we get to the Wiener solution. The algorithm that this uses is the n plus 1th weight is equal to the nth weight plus mu times the error signal into the input signal. In adaptive noise cancellation, what exactly is adaptive? It's the FIR filter. So this is the diagram of the FIR filter that we use. So here we have the input, which passes through a set of delay lines, which are n delay lines as given here, and each of these have a filter weight attached to it. Now this filter weight has this arrow which indicates that it is adaptive, or it is updated every single time the input goes back into the system as feedback. And then the input multiplied by the filter weight generates a summing output, which is y of n. Now when we do this LMS algorithm, we assume that we have a copy of the desired signal. That same desired signal subtracted by the filter output generates the error signal, which is fed back into the input. Now if you can see here, the filter output is essentially a convolution between the input signal and the filter weights. The error signal is the desired signal minus the filter output. Now when we spoke about in the previous slide the LMS algorithm, we said that the n plus 1th weight is the nth weight plus 2 times mu into the error signal into the input signal, that is shifted by I. We'll come to the derivation in the next slide. To derive LMS, we have, say, this example. Now these are a set of 8 filter weights which have W0, W1 and so on till W7. And for an example input, I have taken 48 samples of a sine wave. So that's x0, x1 and so on till x48. Okay. Now like we spoke about earlier, y of n is given by k equal to 0 n into x of n minus k, which is essentially the convolution of these two. So what we do is flip this signal, shift it using a sliding window over this signal. So what we essentially get from this is omega naught into x48 plus omega 1 into x47 and so on w7 to x40, after which it becomes 0. And as spoken before, the error signal is given by the desired signal minus the filter output. The LMS is a least mean square method, which means that we calculate E square, which is d minus y square, and now we can represent y from here as w into x which represents a sliding window or another representation of convolution. So here we have the error square as d square plus y square minus 2dy, which is d square plus wx square minus 2dwx. Now the goal, as we spoke about earlier, is to minimize the total error. So what we do to minimize the total error is to calculate the gradient or the derivative. So we have dfe square by dw, because the filter weights is what we have to change, which we will get here, which we can represent as d by d omega of d minus omega, x w x square, which is 2 times d minus wx into 0 minus x. Why 0? Because the desired signal is independent of the filter weights. So here we have, this is the same as the error signal as mentioned before here. So we have minus 2 times error into the input signal. Now when we use the gradient formula, we had for the LMS algorithm, we had the n plus 1 filter weight is equal to n filter weight plus the gradient, which we just calculated. So we have here minus 2 error, I represent it as n into x n. Now the problem here is this value is too large to subtract from the filter weights. So what we do here is multiply this with mu, which we know as the learning constant or the learning coefficient. This is a very small value, say about 0.05, 0.01, 0.1 or 0.2 depending on the system. So we have n plus 1 filter weight is the nth filter weight minus 2 mu e of n to x, which gives us the algorithm for the LMS filter weight. And this repeats nth time. Now, like I spoke before, the goal of this technology is to minimize the error given by the desired signal minus the previous filter output. Now how they do that is using a cost and function. In this case, the cost function is a least mean square function, and how they do that is using the gradient. Now what the LMS does is uses the instantaneous error. It moves along the error gradient and it updates the weights using this formula, and repeats till we get the minimum possible error, which leads to the most optimum filter weight that was defined by the Wiener's formula. Now the goal is to minimize the error. So the cost function here tells you how far you are from the desired signal. In this case, it is the least mean square. Hence, the function is like a bowl, like a 3D parabolic function. So the smaller the error, the closer the noise that we generate to cancel out the ambient noise, and the closer it is to the ambient noise, the clearer will be the cancellation, and then it makes the noise disappear through destructive interference, and at the end we get a clear signal. Now what we spoke about is theory. So here I have demonstrated a small experiment using a clean signal initially, which is a sine wave, and added some random noise to it, which gives the noisy signal which acts as the input to our adaptive noise cancellation filter. So that input is fed into the LMS algorithm here, and at the end we calculate the signal to noise ratio before the adaptive noise cancellation and after the adaptive noise cancellation, and this is what we get as the output. Now if you can see that the initial noisy signal, you will not be able to tell that it is a sine wave that efficiently, but after using the adaptive noise cancellation, the noise is significantly reduced and you can make out that it is a sine signal. What really shines is the fact of the signal to noise ratio. Initially, it is minus 2.85 dB before the noise cancellation. After, it becomes 10.77 dB, which is a significant improvement. We have the improvement as 13.63 dB, which makes the sound much clearer, which is exactly why adaptive noise cancellation is used in real-time environments. And by this we come to the end of the topic. Thank you for listening, and that's all I had from my side.